Okay, so this is lecture 13. So we start from homework number 13. Okay, so I will just announce our homework from now on. So in the previous lecture, lecture 12, we have talked about how can we calculate the electron density out of the solution of Schrödinger equation. So our procedure in the previous lecture was first solve nonlinear Poisson equation. So when we solve nonlinear Poisson equation, the basic assumption is Ni is exponentially dependent on the electrostatic potential. Also, hole density is exponentially dependent on the electrostatic potential. That was basic assumption of nonlinear Poisson equation. Anyway, we get a certain electrostatic potential profile, and by using that profile, we solved Schrödinger equation. As a solution of Schrödinger equation, we got the wave function and eigenenergy. Since we have knowledge about eigenenergy and wave function, we were able to calculate electron density. There was certain procedure studied in the previous lecture. So now I think that all of you can calculate the electron density as a function of vertical position Z. But since we have started from this assumption, the electron density calculated by this way is not consistent with our basic solution. For example, let's assume certain case. Now, let's say that this is the end of a story. Oh, now we have electron density. Hooray! Now everybody looks happy. But if I ask this question, can you answer? My question is, okay, we have assumed that N is exponentially dependent on electrostatic potential. That was basic assumption. Is it valid? Or it is supported by our solution N of Z? So if we try to whether this relation is whole is valid or not, what we can do is just to say N of Z calculated from this way should be equal to Ni exponential phi over Vt, but this phi over Vt phi is taken from this stage. As you can imagine, actually this relation cannot be valid because when you solve your nonlinear Poisson equation, your electron density, this is your electron density, and this is the position Z, then you found that this is the typical behavior of your electron density. So when you use or when you evaluate this Ni exponential phi over Vt, your solution will look like this. However, you understand when you calculate your electron density by using the solution of Schrödinger equation, what you get is just looks like this. Obviously, this cannot be. This means that this relation or this assumption cannot be validated. So this is wrong. So now we can clearly understand there is or there remains still inconsistency. So how can we remedy this inconsistency? The point is our assumption, the initial assumption of semi-classical electron density and hole density. Actually, this is the main root cause of our problem. Actually, we don't like it eventually. We wanted to kick out this semi-classical assumption on electron density and hole density. In order to calculate the electron density, we needed certain electrostatic potential. That's the reason why, although this is not correct equation from the viewpoint of Schrödinger equation, but we took it. We just took it to make the initial gas available. So now we have electron density. Therefore, we don't have to rely on this semi-classical Poisson equation solution any longer. So we wanted to kick out this relation from now on. How can we do that? So the trick is quite simple and straightforward. Instead of relying on the Poisson equation, which is accompanied with a semi-classical expression for electron density and hole density, we just calculate Poisson equation, or we just solve Poisson equation with the electron density given from Schrödinger equation. Now, this electron density is no longer semi-classical, but it is based upon Schrödinger equation itself, so it will be much better than this solution will be much better than this solution. And by using the solution of Poisson equation, repeat the solution of Schrödinger equation, you will get once again solvent structure, solvent energy, and wave function. And from this information, you can calculate once again the electron density. When you repeat this procedure again and again and again and again, then eventually you will find that the update of your potential, electrostatic potential, will decrease. So when this potential update becomes quite negligible and below your predefined criterion, then you will say, okay, this loop is now conversed, and you will say that this is the conversed and self-consistent solution between Poisson equation and Schrödinger equation. That is the trick. Let me summarize our discussion. So, although we start from the solution of a nonlinear Poisson equation, in this self-consistent Schrödinger Poisson equation, this solution is used just to initiate our Newton loop. So that is just used once, only once. After that, here we have a self-consistent loop repeated several times. Now you understand the self-consistent Schrödinger Poisson equation. So please remember our lecture progress. So there was one milestone, that was nonlinear Poisson equation. I remember that was homework number 10. And today we have homework number 13, which means that the entire system. So that will be homework number 13. So previously we had homework number 12. So what is missing? The missing part is here. The Poisson equation based on the electron density calculated from the Schrödinger equation. That part should be implemented, but I think that you can reuse your previous Poisson equation quite easily, and from this one you can make a self-consistent loop. Then now this is the announcement of homework number 13. In this homework number 13, you may have a certain convergence problem. So that's the reason why I extend the due to not this Wednesday but next Monday. So you have 7 days to solve homework number 13. Please concentrate on homework number 13. And this is nothing but just a repetition of homework number 12. Please calculate the electron density and electrostatic potential. However, in this time, you must get the self-consistent solution. Then, in order to get the self-consistent solution, you have to perform certain self-consistent loop. Here, you have to repeat, and repeat again and again. Then you have to have certain update for electrostatic potential. Please report the convergence behavior of your loop. So as a function of a Newton loop, so just to report the maximum absolute value of your potential update. Then you can find that shows very typical behavior. Please check the convergence behavior of your potential error. The convergence behavior means that here, as a function of your Newton iteration, draw the maximum potential update. That should be shown. I think that once you get the convergence solution, then you can make a comparison between your non-self-consistent solution, which was obtained in your homework number 12, and now you get a new self-consistent solution. So this is homework number 13, and please compare them. So for low gate bias, you will find that actually there is no noticeable difference. However, when you go to high gate voltage, then you will find a significant difference between the non-self-consistent solution and self-consistent solution. Okay? So that is quite important. So please. Okay, so if everything up to now was implemented fine and correctly, then you will feel that this is homework number 13 is just freely given to you. So just copy and paste your Poisson equation and say calculate a new potential. That will give you just a convergence solution and you will be very happy. The point is, if you have made any mistakes in your previous homeworks, then you will find that it is very difficult to make the convergence solution. So that's the reason why I allow 1 week instead of just 2 days. So please concentrate on this homework number 13 and let's finish our discussion about all of them: nonlinear Poisson equation and self-constant Schrödinger-Poisson equation. You know, this is already lecture 13, and we have finished the half of our entire semester, and now we can say our half of our semester was devoted to the equilibrium property of MOS system. Now you can solve the MOS system, double gate or anything for given one-dimensional structure. You can analyze the equilibrium solvent structure. So now let's go to the second half of our lecture in this semester. Yes, so up to now we have discussed about the equilibrium property of our system. Here when I say our system is more or less that is MOSFET, the most important transistor in the world, and now we are talking about non-equilibrium properties of this MOSFET. So simply speaking, we are now talking about the transport problem. So how our charge carriers like electrons and holes are transported from one position to the another position. So the motion in the real space is of our concern. So I can certainly say that this is the central problem of computational microelectronics. This is the single most important problem of our course. So simply speaking, it tries to calculate the terminal currents as a function of the terminal voltages. You apply certain voltages to your system, your transistors, and try to measure the terminal currents of your transistors. For example, usually transistors can be regarded as 3-terminal device or 4-terminal device, and there are 3 representative terminals, so source, gate, and drain. And we can apply certain voltages to gate, certain voltages to source, and certain voltages to drain. After that, since we have applied certain voltages, then there will be gate current, source current, and also drain current. Our goal is to calculate, for example, drain current as a function of applied source voltage, gate voltage, and drain voltage. Also, same holds for source current. We wanted to calculate the source current with given source voltage, gate voltage, and drain voltage. And also we wanted to repeat this procedure with gate current. Okay, so usually that is our goal. So in order to calculate that one, the physical origin of current is motion of charged particle. So when the charged particle are moving inside our system, then that is felt by our terminal. So our terminal reacts to that motion inside the system. I mean that here, I can repeat once again, here and there. Let's say that this is a certain terminal and another terminal, and say inside it there is a certain electron, and this electron is moving in this way. If our electron is moving in this way, although it is not located near this contact, left contact, or right contact. However, its motion can be felt by our terminals, and that motion induce certain current and certain current. So, therefore, the terminal current, it is actually made of the motion of the entire electrons inside our system, and of course inside the entire holes in our system. That's the reason why, in order to evaluate or calculate or predict the terminal currents, we have to understand the motion of electrons and holes inside the system. Some unexperienced students can ask me that question. Okay, professor, so since we are interested with the terminal current here and there, the current is simply given by the integration of current density here or integration of current density here. Why don't you just focus on the problems near contact? But that is certainly not true. Okay, so although we are eventually interested with the terminal current, which is related with unit charge passing through this surface area called contact. However, in order to calculate this quantity related with the terminal current, we have to understand the motion of electrons and holes inside the entire system. That's the reason why we have to solve the entire system instead of just nearby the contact. Therefore, now we have to understand the entire system instead of just half or part of it. So that's the reason why we have to solve or numerically solve the entire system. Then, of course, when you talk about the transport problem, then the most accurate one will be so-called quantum transport. Here, when we say quantum transport, since we assume this one, our charged particles, like electrons and holes, which carry the charge, are actually elementary charges, elementary particles. So they can be regarded as wave. So we have to keep in mind that they are waves. So the wave mechanics is imposed to calculate the transport problem. So that is called quantum transport. The representative method or de facto standard method is non-equilibrium green function method. We'll talk about it at the end of our lecture. So we have still middle October. However, maybe 1 month later or even later, we can have a certain time to discuss about quantum transport. So this is actually the most well adopted method for quantum transport, but in reality, in the industry or in many applications, quantum transport is sometimes widely used. However, for certain areas, it is not used. It is, everybody understands this is most accurate in its physical description, but you know that in order to achieve such an accurate result, we have to spend quite a lot of computational resources. So one thing is efficiency. numerical efficiency. We need to spend a lot of computation resources. But I believe that if only the computational efficiency is the problem of quantum transport theory, then maybe its uses would be much wider than the current situation. The most significant people of our quantum transport theory up to now is consideration of scattering. That is the real problem. So scattering means that by virtue of its construction in this quantum transport theory, we treat our electron and holes as wave function, and there is a wave nature. However, the scattering event breaks the wave nature of our electrons and holes. So therefore, we have to introduce the mechanisms which breaks the coherence of our waves, electron waves or hole waves. So in terms of quantum transport, scattering is not very easy to consider. Okay, so in order to consider the scattering, of course we can do. However, that dramatically increase the computational burden. So it is possible to consider scattering, but compared with just the system without any scattering, the simulation with scattering is much heavier. So let's say that in this case, the simulation without any scattering, and in nowadays even large systems can be addressed by these quantum transport solvers, because we have really good and powerful computer systems everywhere, so you can use it. But point is, our system is heavily determined or affected by scattering, and when we try to consider scattering mechanisms in rigorous sense with quantum transport theory, then you will find that that is really heavy, computationally heavy. So that is, in my opinion, more important problem. Okay, that so-called ballistic. Ballistic here means that the case without any scattering mechanisms inside the system. In this case, it is quite available. Now we can easily calculate the properties under the assumption of a ballistic transport. However, unfortunately, even for our extremely scaled device, like 7 nanometer node, 5 nanometer node, 3 nanometer node, or even 2 nanometer node, although we are talking about extremely scaled devices, but we all understand now there is still non-negligible effect of scattering inside our system. So that's the problem. So this is really a bad news to quantum transport. But anyway, from the viewpoint of a practical viewpoint, that is really certain limitation to be overcome. So okay, usually people are just living in the world of ballistic transport, because so it is very computationally very heavy, and they try to find out certain research topic which can be easily accessible only with ballistic transport solvers. So for example, if we introduce new materials into our industry, or if we try to find out a new candidate for channel material, then we can say, although this is ballistic transport cannot be the realistic one, but it can give us the maximum achievable current out of this new fancy material system. So although that is not the realistic number, a little overestimated, but that is really interesting and meaningful to real world. That was the situation in former times. Like former times means that about 10 years ago or even 7 or 8 years ago. At the time, there was a lot of research activities heavily relying on the ballistic transport. But you know that we are now living in 2020, and in 2020, people are, all of them gave up. So several years ago, they tried to introduce new materials into our MOSFET, so major mainstream transistor. However, we have found that actually silicon and its alloy with germanium, they are the best material system for transistors, at least in this application. So nowadays there is a little research activity to replace the channel material inside the MOSFET. Okay. For example, several years ago, people tried to introduce graphene into our transistor scene. Or graphene has no band gap in it, so it is not a semiconductor, so forget about it. After that, they have tried many two-dimensional materials, so MOS2, or there are long list of two-dimensional materials, and when they publish a paper about those materials, so of course the experimental guys just make a sheet or transistor, very large transistor, out of this new material and report it. That was possible to publish a paper. And from the theoretical viewpoint, we can introduce Hamiltonian related with that new material and calculate the band structure and perform the NEGF, the quantum transport simulation with ballistic transport. Then that gained a lot of attention. So, that is just many years ago story, but please remember that that is now former time story. Now, please clearly understand that we have to still live with silicon, and in that case, scattering is really dominant. Even for two-dimensional materials, in contrast to people's naive belief, actually scattering really dominates the system. So scattering is unavoidable. So that is really important effect. So when we concentrate on scattering, then this semi-classical transport plays a better role. So it can be used where the transport can be regarded as semi-classical. Of course, you can ask me that question. Well, our system is so much scaled, so it is very difficult to treat it as a semi-classical system. Yes, you are right. Our MOSFET is no longer real true semi-classical system. So we have to introduce many features borrowed from quantum mechanics. However, with such a modification, we can still keep the semi-classical description. I'm not saying that semi-classical transport theory is as rigorous or as accurate as quantum transport theory. Quantum transport theory should be the real goal for our theoretical journey. However, in practice, from the viewpoint of an engineer, actually semi-classical transport can be a good compromise between the efficiency and physical description. And you know that I'm talking about from the viewpoint of an engineer. So from the engineer's viewpoint, so we can try to find our certain appropriate compromise. But please note that, of course, in theoretical sense, quantum transport should be our ultimate goal. Okay, so then now let's go to the Boltzmann transport equation. Already in my previous lecture, I have explained it in detail. So please watch that video. So I want to say just one thing. So let's go to this case. So directly go to the result page. So I just change the ways of presentation. If you wanted to see the sequential presentation, then please come back to our previous lecture 12.5. So consider, in this lecture I will just give you the result. Consider certain electron systems. So here we have 1000 electrons at a given time, at the initial time. They are well confined, very short real space range, like just 10 nanometer. Within 10 nanometer, there is 1000 electrons. So how about its density? 1000 electrons per 10 times 10 to the minus 7 centimeter. So this is corresponding to 10 to the 3 and 10 to the minus 6 centimeter. So 10 to the 9 per centimeter. That is the density, one-dimensional electron density of this system. But anyway, we have many electrons confined really a short range, and now they can have uniformly distributed velocities from minus 0.5 10 to the 6 10 to the 6 centimeter per second up to positive 0.5 10 to the 6 centimeter per second. So for velocity distribution, electrons are uniformly distributed within this velocity range. So you know that, in simply speaking, we have a short range. This is just 10 nanometer long, and half of them, 500 electrons, have certain velocity heading toward negative direction, and another 500 electrons are heading toward the positive x direction. Okay, in this case, and we have a acceleration which push our electrons towards the negative x direction. Then what will happen to our electrons, our 1000 electrons after, for example, 1 picosecond? What will happen to them? That is our question. Usually our problem is like this. Now initially we have electrons. We assume that we fully understand the initial position and initial velocity of our electrons. After that, after a short time have elapsed, then what will happen to our electrons? Usually that is of our problem at hand. In that case, in order to evaluate the time evolution of our electrons gas, what should we do is just to apply Newtonian mechanics. So it has initial velocity and we have acceleration. So as time elapses, its velocity will change, and by integrating the velocity within short time, we will get the displacement in the real space. So position and velocity, both of them will change according to time change. So this behavior can be expressed in a plane which have x, velocity. So position and velocity. When I draw like this, in this case, here we have just x-axis, no information about velocity. However, you know that at the same position we have two electrons, and it has initial velocity in this direction and initial velocity in this direction. Then what will happen to these two electrons? After some time later, it will move in this way, and of course this one will move in that way, but there will be certain differences in its position and velocity because initial velocities are different. So in order to predict the fate of our electrons, we need to understand not only the initial position but also the initial velocity. So instead of this real space description, we wanted to add velocity as a description for its state, and we believe that this pair of x, v is enough to uniquely describe the state of our electrons. Okay, so instead of this only x position, we wanted to introduce velocity position. So once we adopt this view, and since this is quite an important concept, so we will name it this space, which is made of both of position and velocity, that is called phase space. Now we have a description in the phase space, and the initial setup of our system is now given by this. The electrons are confined within just 10 nanometer long real space. Okay, they are just all confined in this part. And velocity is uniformly distributed over this range. So we can say that, okay, initially we have 1000 electrons just to occupying this box. So 1000 electrons are there initially. Then now we can solve the Newton equation. So by integrating our Newton's second law as a time, then we can get the position of our electrons in the phase space after 1 picosecond. That is written here as lead box. So simply speaking, that we can find 4 corner points, and these 4 corner points are moved into these 4 corner points after time elapsed. In this case, let me just make a comparison. So think about these 2 points. These 2 points. Here, these 2 points are corresponding to the velocity of minus 0.5 times 10 to the 6 centimeter per second. Initially, it had negative velocity, and its initial position are just 10 nanometer away. This one is 10 nanometer, its coordinate is 10 nanometer more than that left one. After that, they have the same velocity, same initial velocity, and acceleration is the same. And now let's start. What will happen to them? Even after some time later, their difference, position difference 10 nanometer will not change. This difference will just kept as before, because they have the same velocity, same acceleration, and only initial position was different. Okay, so we have 10 nanometer difference. And let me compare once again now these 2 points. These 2 points have the same position, however one was heading negative direction and one was heading the positive direction. And now let's start. What will happen? This one will be accelerated, and this one will be actually deaccelerated. Its velocity will be diminished. Once after its velocity or its speed becomes 0, after that it will move this way. So we can expect that the velocity after certain time later, this one will show larger speed and this one will show smaller speed. So you can see that this one shows large speed and this one shows small speed. However, how about the change or difference of the velocity? Even in this case, the difference of initial velocity is not changed. So in this case, we will have still 10 to the 6 centimeter per second difference in their velocities or speed. So now you can understand, although this blue box looks like a rectangle and this red box looks like a quadrilateral, But anyway, their area in the phase space is the same. So how large is it? Its box area, this blue box area, is simply given by 10 nanometer multiplied by 10 to the 6 centimeter per second. That will be the area. And how about this one? This one is quadrilateral. However, since this side is just 10 nanometer and this height is 10 to the 6 centimeter per second, you know that although their shape is a little different, but area is the same. Then my question is, let's think about a certain electron originally located here. Oh, why don't you introduce more visible color here? Let's say that initially we have this electron. Then when the corner points are mapped into corner points of this quadrilateral, then what will happen to our center electron? Yeah. So what will happen to our center point? So initially it was at the center of this blue box. Then in the red box or red quadrilateral, where will be the position of this center box? Okay, time is up, so please think about it. And I will just finish our lecture today here. And if there is something missing content, then please watch the video lecture 12.5. And in the next lecture, we will just start to derive our continuity equation out of the Boltzmann transport equation. If you have further questions, please let me know through your email. Okay, thank you and see you Wednesday. Bye.